I remind you that in these two tasks we want to find minimum bulk in this graph that have minimum cost. In this case, we when we go in correct direction, we have +1 cost. In this case, when we go through obstacles, we get +1 too. And as you notice, we can create only we can store this graph like weighted graph, and weight of edges will be null if we go in correct direction or don't meet any obstacles, and one otherwise. So we can use null1 BFS for this task, and complexity will be O and M. So we just but we can use not null1 BFS, we can use Dijkstra algorithm, but a little bit changed Dijkstra algorithm. We can create queue deck, and in this deck we contain two in this deck we contain one stack and one queue, and stack will contain the edges that have weight null, and queue will contain edge will have one weight. So in this task we and we in this cycle we support invariant that this invariant we just push back push back to our queue the edge if we move in correct direction, and in this case if we meet the obstacle. So we need to prove that in our queue we contain edges that we have vertices, and we when we store our vertical in queue, we just 1 second, the order of weights will increasing in this queue by vertex. So also we need visited array and in these two tasks, and that's all. We just iterate through all the we just move through in every direction, and we support this invariant in our queue, and we get the answer. and we transform the extra algorithm to null BFS algorithm in such way. I even post this solution because it's very fast. And okay, that's all I wanted to say. Also we can use a star algorithm optimization for queue for stack for edges that we doesn't for vertices that we doesn't that haven't any obstacles or incorrect directions to it. So we can use a star algorithm with Manhattan distance. Where is it? We can use a star algorithm with Manhattan distance to find vertex that in our stack that most близкое to the answer. We can improve this solution in stack. In stack, we just improve it by this algorithm. We can improve it by this algorithm. Okay. Do you understand the idea or not? I think it's quite difficult. Okay. We missed one lecture, and let's one second. I connect my graphical tablet. Okay, let's consider some algorithms. That's a new board. Week 9. We consider prim algorithm and Kruskal. Okay. We considered all algorithms that search shortest paths, but there's a little optimization of all these algorithms. Let's consider bidirectional BFS. Given an oriented graph, unweighted. And we need to find shortest path. In this graph from S to T. Here we have S and T vertices. So in this type of BFS, we launch BFS not only for S vertex, but for T vertex too. We launch it layer by layer, and when we intersect in some layer, we just print this walk that contains some vertex in layer. That's the idea. That was the idea. We launch BFS from S and from T, and from T on reverse stages. In and let after the operation layers are intersect. Layers of BFS are intersected. That means the answer will be in this layer of intersection and mean dist, and we just find this length in such way S and V and V in intersection. And the intersection, just sum it, and that's all. And notice that it less than 2D because there's two layers, and we just the count of iterations is there, but we need to prove correctness of this, so let there's some path that less than 2D. It means on some when we launch our bidirectional BFS, we get that there's suppose we have some paths less than 2D. Here we have D edges, exactly D edges, and here we have D. That means this path is considered with our BFS, and this vertex will be included in intersection. So that's why the algorithm is correct. And why this algorithm is useful? Because if we have a lot of edges and our graph is highly connected, For example, if we have some puzzle, and we start to do with our puzzle some operations, we just we can use only a operations each time, and we want to find a minimal count of how to solve this puzzle using BFS, for example. And that means every time if we have to do X operations, we get that each time we get that we have complexity a to the power of x. And if we launch BFS, bidirectional BFS, we find intersection in this place, and we get only O to the power of x divided by 2 complexity. That's very useful, I think, and we can use not only BFS, we can use Dijkstra algorithm for this task. We can use a star algorithm, and we get less count of operations if we launch our BFS bidirectionally. For example, in task C, in LeetCode task, we can use this BFS. We can use bidirectional Dijkstra, bidirectional null-1 BFS, but this is not very useful because the count of s is less than 4n, and for this task it is not very useful. But if there's more than the count of edge is very big, we can use bidirectional algorithm. So that's all about shortest path. That was all. New topic is spinning tree, and we need some definitions for this. Let's we consider only an undirected graph. In this topic. And G is subgraph of G. No, if just denoted like G less G, G' less than G. If V, obvious, and E' belongs to E. Next definition what is spinning subgraph and spinning tree. Let's G GV is undirected graph. 1 second. And G is G belongs to G less than G if G is spinning tree, spinning graph, subgraph. And if also T is tree, not we just want to use T because we already use it. To less to T spin tree. I thinking about definitions. Is it useful for us or not? We use subgraph, spin subgraph, and spin subtree. Okay. And we just notice that T is subset of edges, and the definition T is minimum spanning tree if of G if Vt equals to sum of UV belongs to T, V UT is minimized. For example, if we have some graph, minimum spanning tree will be like this, or like this, or other, and minimum spanning tree will be we just choose minimum weight of minimum spanning tree of the trees of this minimum spanning trees. So what am I say? Definition. Another definition. Let's A. We need to, for example, we need to build this minimum spanning tree. We need to use some invariant that, for example, we need to use safe edge. Okay, and we and that A is subset of T, where T minimum spinning tree. And UV edge will be safe edge if we use this invariant A of A union by UV belongs to T. In this case, safe edge will be, in this example, safe edge will be this or this. So if this tree is minimum spinning tree, and our task is find minimum spinning tree, and we can use two approaches, two algorithms that uses greedy approach. And this is two algorithms uses only one idea, while A doesn't form a spinning tree. We just add we just find safe edge, that is safe for A. And we just add this edge to our set, and notice that this algorithm will correct because we just use greedy strategy. Greedy strategy is very simple, and but how to do this operation, for example, there's two approaches, two algorithms for this operation. But before we consider these algorithms, we prove safe edge lemma. Let us our spins a graph. That is graph, not tree. That is graph, not only a subset of edges. And T, subset of T, where T is spinning in its minimum spinning tree. T' is minimum spinning tree. And some spinning tree, some minimum spinning tree. We have many minimum spinning trees. And let E cheapest edge, the cheapest edge. Of G. And that edge is bridge of S. Hence S plus E in spinning subgraph 2. Okay, there's useful to consider picture. We have S that contain S's graph and subgraph, spinning subgraph, and this graph can contain connected components, and we just want to, and we consider edge E, and this edge is have cheapest way. So if S plus E S plus this E that contains in our subtree, and this edge is contains in our T, in our minimum spring tree. That is okay. We don't need to prove anything. But there's a case otherwise. It doesn't in T. It means in our spinning tree we have at least one edge that that connects our components, and in this edge, and we consider this walk. We consider this walk and int at least one edge, that is bridge, and we have there. We have here we have vertex in one connected component, in component where okay, in component A, and here we have in component B vertex, some vertex O in V, and we have in T we have some walk in our graph that connect this vertices, which maybe include component or not. And another way, there is edge that contains in our G and not contains in our T, in our spinning tree. So we contain this edges, and this walk and edge, and notice that this walk contain some edge that connects two components, and it means cost Y are greater or equal than cost E, because E is the cheapest edge of G. And we can remove it and add this edge, and we get minimum spinning tree with no greater weight. Hence, our espace E subgraph, spin subgraph, contains in graph that creates from T minus E plus E, and this is our MST. Not that sign. This sign. once again, we consider it safe ledge lemma, and we are going to use this lemma for two algorithms, two greedy algorithms, and we consider two cases. If S plus E belongs to C is okay, it's okay. We consider edge, and otherwise we just say that if there is another edge, it costs greater than our minimum edge, cheapest edge, and we just build our graph with this edge. Is this minimum this will be minimum spinning edge 3, minimum spinning tree 2. So the next we consider MST. We consider Kruskal algorithm and Primus algorithm. Start from Primus algorithm that uses this lemma. Only this lemma. So we consider our graph and some vertex null. We consider all edge from this vertex and choose minimum cheapest edge, and we just add this new vertex one with minimum edge, and we get this and this sets. 1 second. And we just continue this greedy approach, and we just consider two sets and choose the minimum edge, the cheapest edge between these two sets, and just add this edge to our graph. So on, and we get some tree, minimum spinning tree by our lemma. So we consider s equals to null, then for equals to 1 to n, we just find the cheapest edge between two sets, between we call it S. Yes, we call it S, and between our graph without this set. Between our graph without this set, this subgraph, and we just sum at this edge to add this edge to our subgraph. And we proved that with this lemma, this algorithm, this greedy algorithm will be works. So how to implement it? We can implement it using on squared time. We can use the y is on squared because if there's too many edges, it's convenient to use. It's faster to use this complexity because m log n is greater in this case. Okay, of the minimum from S to V. We consider S. We consider some V and all edges that comes from S. We choose minimum. We choose minimum edge, and then if we add this vertex V, we must update all the vertices, all the devs. Let it be okay, we just update this vertices that this devs that the of these vertices. Trying to update minimum, just do reflex operation from V and get on squared complexity, because another edge is already updated. We just need to update only these edges that are new. And there's one more solution. Так, if binary heap on the in this case we just initialize our source with plus infinities, and with plus infinities, and we just do what? We just do extract min. And then we do decrease k. If there's we update our minimum, we just use decrease k. Let me consider. Let me paste picture to mirror desks. is this useful animation. What we do, we just every time we just choose minimum match from this set to these vertices and just add it. We can update by on squared this edges, this vertices, and we can update. We can create heap, for example, and contain in this heap we contain vertices that we doesn't visited, and choose minimum match every time, each time. And there is a better complexity if we use, for example, Fibonacci heap. Instead of binary heap. I think it will be better if I write pseudocode, because it's not very obvious, I think. So we just iterate through all the vertices. We just initialize our source. I think так, one more time I write it how to initialize either single source or not. Okay, I don't do it. We just initialize our source. You can consider this in previous lectures. GVR for initialize our source, and we just say that our heap is equals to VG. We just contain our heap, all the vertices, and while q is not empty, we just extract min by dv. Extract min by dv. And for each edge, for each v belongs to GU, we just say that if v in Q and v do relaxation. We just do relaxation with the v. Then Okay, and we and how to get minimal spanning tree? We create an array P, and in this array we contain our tree. We just say that P PV equals to U, and in this array we get our sequence. Okay, next algorithm, cross-cult algorithm. It is very simple. We just iterate through. Through edges. We choose greedy strategy. That's why we're going to iterate through the edge in ascending order. And we just add the edge from our sequence if the edge doesn't create cycle. Так, if the edge we just add them to the answer. If edge doesn't create cycle, and it's clear to see that we're going to do it until the count of edge less or equal less than n minus 1. That's all. That's all the algorithm. And to do it, we just use for example, we let I paste another picture again. Wiki in this strategy we just add edges. The weight means length in this case, and we just add this edge while we don't we add this edge, but there is a cycle. Okay, when we add this edge until we don't get that count of edge is equal to n minus 1. Okay, and very simple algorithm. But for this iteration, but we can use strategies that we create some array color or SCC, and in this array we just contain the number of components, and if SCC if SF web belongs to some strongly connected component, we just trying to union these components, or if there's an edge between them, that means these components, the edge vertices that contains in one component have the same SCC.